Thank you very much. So, thank you very much, Tony, for, introducing my talk. I will talk about 7 transmembrane helices. And I want to start with an analogy about pseudo-symmetry. You can see here a masterpiece from the Renaissance at the Vatican. And there is a universal principle here. Plato's academia basically started with Plato. And then his student, Aristotle, ended up creating the other half of the School of Athens. So there is a universal principle of duplication here, and then eventually fusion, although this fusion of two antinomic semi-schools, if you want. If you see, Plato is having his hands towards more idealistic matters, while on the other hand, Aristotle is showing down to earth. And even in mutations, you can see that they have here, the god is Apollo, while here is Minerva, the god of war. So when you're talking about down to earth, it seems like Aristotle might have won when we see the world today. But that's aside the purpose of today. So the other thing that was written normally, according to the legend, on the door of the Academia is, "Let no one untrained in geometry enter." So I think this audience knows about geometry, and therefore I'll talk to you about now the analogy to the 7 transhelical membrane proteins, and in particular GPCRs, and what we can learn from them. So we're going to decompose the 7 TMH proteins into protodomains of 3 transmembrane helical protodomains. And then we'll look at these protodomains and see that they are actually very idiosyncratic. And then we move to quaternary structures, and even the concept of a supradomain as opposed to a protodomains, with the same exact dynamic, this time, symmetric dimerization, and the model that is emerging for GPCR of rolling dimers. And then this will raise questions about protodomains as precursors in this, usually accepted duplication fusion model. But there is always a problem of a dilemma of convergent versus divergent evolution. And then we can eventually, venture into the idea of conformational evolution, which would raise the bar for evolutionary models. So effectively, like in 2014, we did a survey of the database at the time, and we found that all classes of scope classes of domains, I don't think it works, A, B, C, D, for those who don't know, is all alpha, all beta, and then the alpha, beta, alpha plus beta, and then F is grouping the membrane proteins, which are 2/3 helical, 1/3 beta. And in the survey, as you can see, there was always the highest the fold with the largest number of superfamilies in it that was symmetric, that came first was A24, like myomeratrine, B1, like immunoglobulins, C1, like the timbarol, D58, like ferredoxin, and actually GPCR didn't show up. Many membrane proteins showed up, like you see the highest score is 24%, but not GPCRs. While before we had the program, like CSIM, I had found these kind of symmetries by hand. Now, before we go to membrane proteins and to helical proteins, here is a depiction of an immunoglobulin. And it's something that is of very high interest for us at the NCI, because, of course, with immunotherapy, we need to engineer many of those. And that, you can see that there is not only it's a symmetric, but the symmetry is created by the docking of the two protodomains here on the left and the right, in an anti-parallel way, by the way, with a self-complementarity of the similar strands. And that is very important, because you find that over and over and over again. Symmetry is not a cause. Symmetry is a result of a cause. And that is about self-assembly and self-similarity of protodomains in the case where domains are actually linked by a linker. Now, just to show you that this is universal, here are two RNA protodomains in a ribose switch. And if I have time, I'll show you more interactively how you get these kind of things. So going to GPCRs, I'm not going to use too much of the 3D depictions that you have on the left here. I'm going to color code the first strand, the first helix in blue, the second in magenta, the third in orange. And there will be some green for the binding residues and some actually cyan for those binding a G protein. Here I took on purpose an example of an active conformation of a GPCR, because we might lose symmetry between the protodomains, but the protodomain will still superimpose with mRNAs. And so if two transmembrane helices are actually in contact, regardless of the orientation is more, it's not perpendicular to the membrane, but even if it bends 45 degrees, I will use this kind of depictions. And you can see an axis of symmetry here, and we'll go over many things. Now, this is the kind of things that programs cannot do, that aligning protodomains exactly as accurately as you can, and then you can start seeing patterns. In particular, in the TM3, TM7 part, you see the always or almost always a pattern like that binding ligands. Now, it's very interesting that now we have, class C, class A, class B, class F, and actually they're all lining up between 1.7 and 3.5 angstrom RMS for the aligned residues. And then when you take, structure by structure, you usually are between 2.5 and 3 angstrom. So that is how you can compare protodomains that assemble symmetrically. So there are many, many membrane proteins, many we don't know of, but that do share this triple helical bundle. And so we actually looked at the study over a number of them: the sweet protein, the PNUC, and the trick that was solved not too long ago, FOCA and aquaporin, and so forth. And some of them are in parallel, like it was very well described by Tony, and some of them have an inverted topology. And one of them, MFS, had actually not only an inverted topology, but an intertwined inverted topology. I will not have probably time to go over everything, but so you can see a protodomain here, duplicating here, and it's always the same, duplicating here, duplicating here, duplicating. And they all have a tendency, when they form symmetric domain, to also form asymmetric domain oligomers of higher symmetry. So the overall symmetry of protodomains and oligomers together will give you up to, let's say, in this case, for example, a D5 symmetry. Now, for those interested in RMS, you can see that exactly like for the GPCR, we are in the same range for all of them. Now, semi-sweet is a very nice example because it's a bacterial protein. It's a triple helical membrane protein that actually forms dimers. And then when you go to eukaryotes, well, you do have in a parallel orientation, you do have the same exact arrangement with a false helix that actually serves as a linker so that they don't invert. And at the same time, you can see that they nicely form trimers. I have a problem with this one. And you can see the patch that represents number 4. Okay, so in terms of sequence, you can see, especially on TM2, TM3 versus TM6, TM7 here, you can see quite a nice match between the 2 protodomains of the suite versus, let's say, one domain of 3 helices coming from the bacterial version. Now, the first one is actually obviously moved a little bit, and you can see that here we have a very low RMS. It's a little higher when you're using the 3 of them. Now, a question that was raised by the author of these structures is with another structure called NUC. I don't know if I pronounce it right. But as a monomer, it has a completely different topology, but it still binds sugars. So the same function led this guy to think that these NUC and suite might be related, evolutionary. They also form trimers, but if you remember the trimer before, they're completely different. So when comparing the two, they say that if you ignore the topology, well, you have a very good match. I mean, this is true. You can align this 1, 2, 3, 5, 6, 7 in a very nice way. But actually, if you put the technology, if you put the topology like we did for superimposition, you get over 5 angstrom RMS difference. And some other author before that were actually suggesting that the NUC plus suite plus actually GPCR belong to a same superfamily called TOG. Well, we don't buy into that. Here we have actually also a very different topology between the 2 NUC and GPCR. One is clockwise, and the other one is anti-clockwise. So one thing that when you observe these protodomains across domains, and not just for membrane proteins, you find that they are idiosyncratic. A protodomain usually will define a domain uniquely. Very rarely will you find a protodomain that can match another substructure in a non-symmetric domain. So here, you can think about a conformation that actually can vary quite a bit depending on the residues involved. And then you can also think that you can build symmetric domains in many, many ways by searching for a match. And when you search for a match, it will be a symmetric match very often. And in a case like this one, 1, 2, 3, you might end up forming a clockwise. It doesn't take much to actually bring it to counterclockwise, which would be like a mirror image.
2 minutes.
I'm sorry?
2 minutes.
Wow, 2 minutes. So let me actually go to one example where the program works very well. And CSIM can give you, for GPCR, which is an obligated dimer, it can give you not only the quaternary symmetry, but also the internal symmetry. So the programs can, in some time, give you the result. Now, I have many things to tell you, but the most important one is that we have now a dimerization interface that's been demonstrated by Fret and Deer experiments, where actually a monomer here can form a dimer in symmetric ways, and you can see many proteins are showing that in structure. And you can see that here you would have actually conformations that would block the G protein binding, and so forth. These are all seen in crystal structure, but they've been demonstrated that they are dynamically related. And so therefore, during the time of the dimer lifetime, they sample the different conformations of the dimer that we just saw here, a snapshot here. And since I don't have much more time, I will not be able to go into venturing into conformational evolution, but we have actually a poster that will talk to you about different parts of the evolutionary relations between the ligand binding part and the G protein binding part, and also many things about a model that we might have that would be an asymmetric swap between four transmembrane protein helical proteins that would actually eventually be a precursor of GPCRs. I don't have time to go into that, but we have learned many things that we can tell you on the posters. Ravi Abrol will be there at B538, and I will be showing these things more interactively in 3D in another poster, 506. Now I would like to thank not only Ravi, with whom I enjoyed working, but also especially Jaya Wang and Tom Madej at NCBI, who've been writing a lot of software, and Tom is working on the symmetrical part now. Guido Capitani, that passed away unfortunately, that had accompanied us for a while. And Tom Mistelli especially, that allowed me at the NCI to continue that work. And with this, I thank you for your attention.